Hi there, folks. Today we're looking at components of polynomial graphs. So we're going to start talking about the graphs of polynomial functions and the different things that we look for as we look at these graphs, as we look at these curves. And the first thing we're going to talk about is increasing and decreasing, all right? Increasing versus decreasing. Increasing is when y is going up. So when we talk about increasing and decreasing, we're talking about visually the y values. Is the function going up or down? All right. So if y increases as x increases, we call that increasing. All right. Decreasing is when y decreases as x increases. And notice they both say as x increase. That's just a fancy way of saying going left to right on the graph. If you think about it, for x to be increasing, the smallest x values start at the left of the graph and the biggest x values are at the right of the graph. So x increasing just means going left to right on the graph. All right. So another way to state this would just be to say, hey, as we go from left to right, if the function is going up, that's increasing. As we go from left to right, if the function is going down, that's decreasing. All right. And the idea of identifying increasing and decreasing visually is really easy. All right. The thing that students struggle with is we can easily identify increasing and decreasing on the graph, but labeling it is a different story. We label it in terms of its interval, all right? So visually, we see increasing and decreasing in terms of y going up or down, but we label it in terms of x, okay? We visually see it in terms of the function going up or down, but we label it in terms of left and right, okay? And you'll see that in a moment when we get to the graph. That's the thing that's tricky, is the labeling, all right? Because we label it kind of using a different component, using a different dimension of the graph than we use to identify it, okay? Talking about relative maximums and minimums. A relative maximum occurs when the function goes from increasing to decreasing. We talk about these in terms of turning points, and really this is a foundation. Some of this stuff we're talking about right now, this is some of the stuff that you're going to explore in calculus, all right? This is the foundation for some of those pieces. So increasing versus decreasing, really it's a change direction. Relative maximum, it changes direction, all right? It was going up, now it's going down, all right? So we get this kind of high spot, all right, on the graph. And then a relative minimum is the opposite of that. It's when we go from decreasing to increasing. The function was going down and now it's going up, so I got a low point on the graph. And the reason we refer to them as relative maximums and minimums is because they might not be the lowest value on the graph, okay? Yeah, so a relative maximum might not be the highest value, and the relative minimum might not be the overall lowest value, all right? But the relative maximum is higher than the points around it, okay? It's a high spot, not necessarily the highest point on the whole graph, but the highest spot around that area, okay? When you think about that idea of relative, like if you've ever met me, I'm not a real tall guy. I'm at like 5'7.5", all right? 5'8" if I'm really stretching my neck out, okay? So I'm not extremely tall, but if we were comparing me, if I went into a kindergarten class and we compared the heights of all the students and threw me into the mix, I'd be enormous. I'd be huge. I'd be really, really tall. I would be a relative maximum. Okay, so even though my height wouldn't be considered a maximum when you look at the entire population, I would be a relative maximum in that room because I would be the tallest, okay? I would be the tallest compared to what was around me, all right? That's the idea behind a relative maximum. And same thing with a relative minimum, okay? If I went to the same thing, taking my height, if I went and stood in a room with NBA players, I would look incredibly short because I would by far be the smallest person, the shortest person in there. I would be the relative minimum in that scenario, okay? Even though I'm not the shortest person on the planet, I'm not extremely short in terms of the overall population. In that room, I would be considered the absolute minimum, okay? Because I would be shorter, I would be the minimum compared to what's around me at the moment, okay? That's the idea of relative maximums and minimums, okay? So we just look for those turning points. Where do they go from increasing to decreasing or decreasing to increasing? And then the end behavior. This is a pretty tough one, but the end behavior is what happens on each end of the graph, okay? That's why we call it end behavior. If you think about how the graph behaves on each end, Well, that would be the end behavior, okay? And once again, this is one of those things that we identify the end behavior in terms of why, all right? We talk about it in terms of, okay, on one end, is it going up or down? On the other end, is it going up or down? Is it going to positive or negative infinity? But we check it and we talk about it in terms of x as well. So the end behavior is kind of defined here in terms of x, but we look at it and we finish labeling it in terms of y. And so, again, don't be alarmed here by this notation. It says the end behavior is what the graph does as it goes to as x approaches plus or minus infinity. Well, that's just a fancy way of saying left and right. When you think about it, negative infinity just means, hey, that's as far left as you can go. All right. So as the function goes to the far left, what does it do? And positive infinity, well, that's just going right forever. And as the function goes to the far right, as it goes to the right forever, what does the function do? Does it go up or down? Okay? And so let's look at a graph here and let's identify some of these things. So increasing and decreasing, all right? Increasing is when the function is going up and decreasing when it's going down. And again, that's as x increases, so that's as we go left to right. So as we go left to right, if I were to kind of trace this function, let me trace it in purple. As I go left to right on this function, here's the path that I follow. See, look, I'm going up, so I must be increasing. Then all of a sudden it changes. Now I'm going down. Let me change colors, so now I'm decreasing. And now I'm going up again. And so as I follow this function left to right, I'm increasing. And it's really easy to identify. I can circle on the graph, say, hey, increasing, increasing. Those are the spots where it's going up as I go left to right, okay? And then in the middle here, decreasing. Really easy visually to identify increasing and decreasing, okay? But now here's the thing. We identify it in terms of the y values, in terms of the dimension of us going up or down, but we're going to label it in terms of x. I want to know the interval on which this thing is increasing. And so if I looked at that first purple section, the up and down tells me that it's increasing, but I want to label where it's increasing, okay? And if I want to label where it's increasing, well, I think about it and I say, okay, well, it was increasing until I got to this point right here, and then it was increasing to the left, right? So everything to the left, on the left side of this graph is increasing. And so when you think about that in terms of an interval, where did it start increasing? Because again, I went left to right on this thing. Well, if I think about where it started increasing over here in this section, I have to keep going to the left forever, right? So if I go to the left forever, that's where it started increasing. It increased from negative infinity until I got to an x value of -2. Okay? And sometimes what I like to do is I like to kind of think about this in terms of a timeline. All right? You think about this in terms of a timeline. The function started at the beginning of the function, at the beginning of time, at negative infinity. The function started off increasing. And so as we kind of look at this thing, break it down this way. Let me draw a little timeline down here. So here's the timeline of the function. And the timeline always starts at negative infinity and ends at positive infinity. And just think about this function in terms of the timeline. As I go from negative infinity, as I follow the timeline of the function is going up. We're in that purple section. And the function continues to go up until I get to this spot on the timeline, which is at -2. And then the function goes down until I get to this spot on the timeline, which is +3. And then the function is going up again as I continue to go to the right. And so as I continue the timeline, the function is now going up for the rest of the function's life, for the foreseeable future here, so positive infinity. And so as I think about that in terms of a label, it was increasing from negative infinity to -2. Again, I label it in terms of x, and I'd use a parenthesis here because I can never actually equal that. The -2 is maybe up for debate here. And as you look at this, well, -2, when you think about it, that's actually a relative maximum. And when we're at the maximum, is the function going up or down? That's the question. And the answer is it's doing neither of those things, okay? That's the moment where it's not going up or down. It's the moment where it was going up, but now it's going down. It's that moment in between. And so we're going to put a parenthesis here because we say, hey, you know what? It's not actually increasing at -2. That's when it stopped increasing, but we don't include that, okay? See, that -2 is where it stopped increasing and started decreasing. That's the relative maximum. And though the other place that it's increasing was from 3 to positive infinity. And once again, it's the same kind of deal, parentheses all around, and then that union symbol, okay? But now decreasing, it was decreasing from -2 to positive 3. And again, parentheses for each of those because those values aren't included in the increasing or decreasing. They're the relative maximums and minimums, okay? And so when you fill this out, if you're really struggling with this, fill it out like a timeline. Say, hey, from here to here, the function was going up. So I'd go -infinity to -2, and I put it in the increasing section. And then just do the next section, -2 to 3. It was going down, so then you list that in the decreasing section. And then from -3 to positive infinity, it's going up again, so then I list that in the increasing section, and then go back through and fill in your union symbols if you have to, okay? But again, we identify increasing and decreasing in terms of y, but we label it in terms of x, and I think that's where students really struggle with this, okay? Relative maximum, we're just looking for kind of high spots. They're pretty easy to identify, and we can see there was one right here. That's where the function changed from increasing to decreasing, and so that's a relative maximum, and that's an ordered pair. That's a point that I'm referencing. That's the ordered pair -2, 4. And here's that situation where I see a lot of things that look like ordered pairs, but please understand that this one is an ordered pair because of the context, because a relative maximum is a point, okay? But this is interval notation because I'm talking about an interval on which this thing was decreasing, okay? A section of space where it was going down, okay? And then a relative minimum. This thing changes directions over here. It was going down, and now it's going up. And this is the point right here. At 3, -2, that's the point where it went from going down to going up. So that's a relative minimum. And one of the things I really like about this example in terms of relative maximums and minimums, when you think about it, there are bigger points. Like when I look at that relative maximum, there are bigger points on this function. Like right here. This point right here, that point is higher than the relative maximum that I identified, okay? There are bigger values on this graph. There are maximums above that relative, okay? But that point is bigger than all the points around it. If I only looked at the points on either side, that one's the highest, okay? It's a maximum relative to the points on either side, okay? And the minimum, same kind of thing. There are smaller values, like right here. That's a smaller value on this graph, okay? That is a value below that relative minimum. But this one is the smallest compared to the points around it. It's relatively a relative minimum, okay? But that slight distinction. And then end behavior, I just look at each end, okay? And here's the thing. When I look at the left side, that's where x is going to negative infinity. So on this side, that's x going to negative infinity. So I label it like this. I just say, hey, as x goes to negative infinity, and I say that because I can't equal negative infinity, so I say x is going to negative infinity. Well, let's talk about what y does on that end. On that end, what's the function doing? Is it going up or down? Well, the answer is it's going down. So then I would say f of x, or y, is going to negative infinity. So essentially, this is a fancy way of saying, hey, on the left, this thing is going down, okay? And when we translate that into math speak, the left is x going to negative infinity. And going down is f of x, the function going to negative infinity, okay? And then if I look at the right-hand side, if I look at the other side of this thing, again, the right-hand side is x going to positive infinity, okay? And that's just a fancy way. X going to positive infinity is just saying, hey, the right side of the graph. And that thing is increasing, it's going up at that end. So f of x is also going to positive infinity, okay? This is the notation we use. And again, there's no equal sign because we can't equal an infinity, all right? We say the x value is going to this, and the y value is going to this. This is where it's headed. This is how the ends are acting, okay? And please understand, this translates into, you can translate into left and right and up and down. It means the same thing, but this is the mathematical way of expressing it, okay? If I look at this next one, same kind of thing. If I just kind of follow along this function, I can see that it's going up, left to right, and then it's going down, and then it's going up again, and then it's going down again. Okay, so as I kind of trace this function and just look at it in terms of increasing, decreasing, I can see that it's increasing here. And again, I look at it visually in terms of increasing, decreasing. I'm looking for y. But let's label in terms of x. Again, think about the number line if you have to. Negative infinity to positive infinity, that's the life of the function. Let's see, it was going up until I got to here. So negative infinity to negative 2 was increasing. And then from negative 2 until I got to here, until positive 1, well, there the function was going down. It was decreasing. So that would be in the decreasing section. Doing the other version this time. And then from 1, it started going up again until I got to here, which is a positive 4. So from 1 to 4, it was going up again, so that's increasing. And then after 4, it was going down, and it keeps going down for the rest of this thing. So from 4 on up, from 4 to infinity, the function is going down again. Okay? And then I slap my union symbols in between. So I think about it in terms of the life of the function. From negative infinity to positive infinity, what's the function doing? Where's it going up? Where's it going down? I'm labeling the where. That's why I'm labeling in terms of x. Okay? Where is it doing this? Visually, I can see what it's doing based on y. Okay, but I label it in terms of x. Where is that happening? Okay, and then relative maximums. There's actually two of them. There's a relative maximum right here at negative 2, 3. And there's another relative maximum right here at 1, 2, 3, 4, 4, it looks like. And it's okay to have more than one relative maximum, all right, because again, it's relative to the points around it. And then relative minimum, there's one of those right here. That's at 1, 0. And now end behavior, I look at the, as x goes to negative infinity. As I look at the left-hand side, the function is going down. So f of x is also going to negative infinity. And then the right side of the function, as x goes to positive infinity, that's the right side of the function. The function is going down on that end as well. So f of x goes to negative infinity again, okay? But we're just labeling the different aspects of this graph, okay? All right, so evaluating with infinity, this is what we use to determine the end behavior from the equation. So we've kind of looked at all the components of the graph of a polynomial function. Now we want to look at the equation, be able to identify some of those components so that we can start to graph these things. That's kind of where we're headed here. All right, so evaluating with infinity, essentially when we plug infinity in, and really, again, infinity is more of a concept of a number. It's not an actual value. So when we plug infinity in, we're just trying to ask ourselves, hey, if I plug a negative infinity in, what happens when I plug in smaller and smaller, bigger and bigger negative values, okay? What happens when I plug in larger and larger values for a positive infinity, okay? And so it's not like we're actually plugging infinity in. We're just thinking about if this value got closer and closer to infinity, what would happen to the overall function, okay? And so a lot of times what happens here is the function kind of goes to one version of infinity, either positive infinity or negative infinity, all right? And what it really comes down to is this kind of becomes almost just looking at the signs of different things. If I plug an infinity in, I know I'm going to get a version of infinity out. I just need to figure out if it's going to be a positive or a negative infinity, all right? And so think about how we get positives and the negatives with other numbers in terms of exponents, in terms of multiplication. Infinity is going to work the same way, okay? For example, if I look at something like this guy, we want to evaluate the end behavior. And essentially evaluating the end behavior is what happens as x goes to positive or negative infinity. So I just want to evaluate for plugging a negative infinity in for x and then a positive infinity in for x. Again, I have to use this notation. I say x approaches negative infinity, even though it's like I'm plugging in negative infinity, and I can't actually equal negative infinity. I can't actually plug it in. So I think about what would happen as I got closer and closer to negative infinity, all right? I write it in a manner, so I write it like this, as if I'm plugging in a negative infinity, all right? But again, to evaluate this, I just ask myself, if I have a negative value raised to the 9th power, well, it gives me a negative value. And if I have a bigger negative value, like a negative 1 to the 9th power, be a negative 1, okay? But if I had like a negative 5 to the 9th power, it would give me a larger negative number. If I had negative 10 to the ninth power, it would give me an even bigger negative number. And so when you think about it, as I plug in bigger and bigger negatives, raised to the ninth power, I get bigger and bigger negatives. What that's telling me is that negative infinity to the ninth power, as that value goes to negative infinity, raising it to the ninth power also takes me to negative infinity, okay? When I get closer and closer, when I get more and more towards negative infinity, raising those values to the ninth power still gives me bigger negative values, so that heads towards negative infinity as well, okay? And now right here, if, once again, negative times a negative, we know that's a positive. With infinity, it works the same way. It's going to be a positive infinity, but think about it. If I have bigger and bigger negative values and I plug those in, negative 1 times negative 32 is a positive 32. Let's go closer to negative infinity. Negative 2 times a negative 32 is a positive 64. And see, if I plug in bigger and bigger negative values, times the negative 32 gives me a bigger and bigger positive value in the end. So I say negative 32 times negative infinity is like positive infinity. And really, hopefully you recognize this as, oh, it's just signs, okay? Any negative number to the ninth power is a negative value. And now any negative times a negative is a positive. So f of x, the y, is going to approach positive infinity, okay? And so if we just kind of think about it in terms of signs, I want to do the positive infinity next. So as x goes to positive infinity, and again, I don't say equals because I can never actually equal that value. I'm saying, hey, if I got closer and closer to that value, if I was able to make it there, this is what would happen. So positive infinity, well, any positive number to the ninth power is still a positive number, so it would be positive infinity. And now negative times a positive, any negative number times any positive number is a negative number, so it's going to be a negative infinity. And that's it. That's what it comes down to. And if you realize that, then you're just dealing with signs, and you're asking yourself, okay, is it going to be positive or negative? Okay? The other thing we have to look at is something like this guy, all right? For something like this, it seems like we have opposing forces. Like, so if I plug a negative infinity in here, one of them is going to have be squared and then multiplied by negative, and one is being multiplied by a positive. So when I add or subtract those, what's going to happen? Well, the fact of the matter is that one of these things is going to get so much bigger than the other that one of them becomes insignificant, okay? And so here's what happens. So let me use an example. If I plugged like a 1 in, think about the values you get here. So like 1 squared is 1 times a negative 3 is a negative 3 and a 6, okay? And right now the 6 is bigger. But let's plug a 2 in and see what happens, okay? If I plug a 2 in here, all of a sudden, oh, they're the same, okay? Because that first one's growing faster because it's got a bigger exponent. Ready? If I plug a 3 in. Let's see, that's going to be a 9 times a negative 3 is a negative 27 plus 18. All of a sudden, that negative value is bigger. And so if I plugged in bigger and bigger values, think about where this is going. As I add these together, it's going to get more and more negative. What happens is this original guy kind of takes over. Here, let me jump way up. Let me jump to like a 10. All of a sudden it's 60. Over here it's negative 300. See how much bigger that negative is than the positive? So what happens is the larger exponent kind of dominates this thing. All right? The larger exponent controls which way it's going to go. All right? It doesn't matter what that 6x is doing. All right? That x squared becomes so much bigger, so much faster that it is going to determine whether this thing goes to positive or negative infinity. Okay? And my point in saying that is to say this. When you go to plug this in, when you evaluate for infinity, you just use the thing with the biggest exponent, okay? Nothing else matters. At some point, the thing with the biggest exponent gets so much bigger than everything else that nothing else in the function matters. And we saw it just with plugging a 10 in. That thing was huge compared to the other one. If you plug 1,000 in there, then the thing with this, the 6 times 1,000, 6,000 is going to be nothing compared to the negative value I get, okay? And so again, when we evaluate for infinity, because we're going to these extremes, the larger exponents take over. I only have to plug it in here, okay? So let's plug a negative infinity in. And again, I'm going to do this in our heads this time. If I have any negative number squared, it gives me a positive number. Well, actually, let me write it out one more time. Any negative number squared gives me a positive number, so that's positive infinity. Now, negative times a positive, any negative times any positive number is a negative. So I end up with a negative infinity, okay? Same thing with the next one. If I plug a positive value in, again, any positive value squared is going to give me another positive value. So it's positive infinity. And now any negative times a positive is also a negative. And that's it. And so as we look at these two functions, we already know what a piece of the graph looks like for each of these. Like that first one, on the left side, as x goes to negative infinity, the function goes up. And on the right side, as x goes to positive infinity, the function goes down. For the one we just looked at, on the left side, the function goes down, and on the right side, the function also goes down. So I'm already starting to describe what pieces of the graph are going to look like, okay? If I look at this one, again, if I'm plugging infinity in, one of these things is going to get so much bigger, so much faster that everything else kind of becomes insignificant. When I evaluate for the end behavior, I only look at the thing with the biggest exponent, okay? That thing is going to take over, it's going to take control. So I'm going to plug it in here, ready? So as x goes to negative infinity, again, I'm raising it to the fourth power. Any negative value to the fourth power gives me a positive. So then if I have a positive times a positive, because it's a positive 8, it's still going to give me a positive infinity, okay? If I were to plug a positive value in, once again, any positive value raised to the fourth power is going to give me a positive value. So infinity to the fourth power is still going to be positive infinity. And then times a positive 8, well, positive times a positive is always a positive. So it's still going to be positive infinity, okay? So this one on the left, it goes up, and on the right, it also goes up. If I look at this guy, once again, the only thing that ends up mattering is the thing with the biggest exponent. That's going to take over. That's going to determine which way this function goes. And so if I plug negative infinity in, once again, any negative value to the third power gives me a negative value. So negative infinity to the third power is a negative infinity. And now any negative value times a negative 2 is going to give me a positive. So negative infinity times a negative 2 is a positive infinity. All right? Now I plug in a positive infinity. So as x goes to positive infinity, once again, any positive value to the third power is a positive. And then times that negative 2 is going to give me a negative. So this is going to give me positive infinity when I raise it to the third power, and then times the negative 2 is a negative infinity. All right? And so again, as I look at this thing, it's just telling me that on the left-hand side of this thing, the function goes up, and on the right side, the function goes down. Okay? All right, and then taking a look at this last one, the problem is that this thing is not in the right format, not in the format we're used to. I can't see the degree or the leading coefficient because this thing is in factored form. So what I would normally have to do is kind of multiply this thing out, but keep in mind the only thing I want is that first term, okay? And so first of all, if I think about multiplying out this entire thing, I don't want to do that because it would be a real pain to be perfectly honest with you. But if you just kind of think about multiplying this guy out to start. If I did x minus 1 times x minus 1 times x minus 1 times x minus 1, yeah, I could multiply that all out. But since the only thing I care about is the first term, think about it this way. If I have all of these lined up and I only care about the first term, well, then let's just multiply all the first terms together. And if I just multiply out the first terms, what I would get is an x to the fourth. And yeah, that'll be one of the values when I multiply this whole thing out. If I multiplied all of it out completely, I'd have a bunch of other values after that. I would have an x to the third and an x to the second. But again, I don't really care about those values, all right? I only need the one with the biggest exponent. So the shortcut that I go through here is I just think about the first term. I say, you know what? I only care about the first term, so I really just need the x to the fourth. Yeah, there's a bunch of other stuff there, but who cares about that stuff, okay? And then when I multiply that by the x minus 1, I kind of follow the same procedure. I look at this and say, okay, I'm going to distribute the x and distribute the 1, and yeah, I get a bunch of but I only care about the first term, so let's just multiply the x times the x to the fourth, which is x to the fifth. Again, I ignore everything else. I don't care about it. I only care about the thing with the biggest exponent, so I'm trying to find that thing. And so as you think about multiplying all this out, all right, and yeah, again, if I multiplied it all out completely, I'd have an x to the fifth with a bunch of other terms behind it. But again, I don't care about those other terms. And then I would distribute the 3x squared, and the first term it would give me is a 3x to the seventh. And yeah, there would be a bunch of other terms after that. But again, I don't care about the terms. I only need the one with the biggest exponent. All right. And so as I think about this thing, sorry, let me erase all this. If I multiply out just the first terms, it means the first term of the polynomial after it's all multiplied out is going to be a 3x to the seventh. okay? So now I can see the thing with the biggest exponent. I can see the leading coefficient. That's all I need, all right? And so now I plug in my infinities. If I plug a negative infinity in, again, any negative value raised to the 7th power is going to give me a negative value, and then negative times a positive 3 is a negative, so it's a negative infinity, all right? Again, I'm really just focused on the signs at this point. Now I plug a positive infinity in. Again, any positive value raised to the 7th power gives me a positive value, and then times the positive 3 is still a positive value, so positive infinity, okay? And so by looking at this thing, I can tell now that on the left-hand side, this thing goes down, and on the right-hand side, the thing goes up.